So in the last video I was talking about the LU decomposition. So we have this matrix, and then we are decomposing it, and then I have explained this format. So after you execute this command, then you have the three values LU, P and C. So let's see what's included in LU. So we can display it in the matrix form like this, so which is the same as these values over here. So our L and U matrices will come from this LU matrix. So for this LU matrix, then we have to extract the lower triangular matrix. So for that, what we can do is we can define the lower triangular matrix by this symbol L, and then we will use the lower triangularize command with a parameter -1. That means we don't want the diagonal elements over here to be like these -3, 4 and 2. So diagonal elements will be 0, 0, 0. And then in order to make these diagonal elements 1, 1, 1, we will add the identity matrix 3 by 3 to that, and then we will get the lower triangular matrix from this LU. So this will be the result. Okay, 1, 0, 0. So 1, -2, -3, and then you can see that by the manual method, the lower triangular matrix, the first column elements will be the one that will be divided by this pivot position. So -3 by -3, it will be 1, and then 6 by -3, it will be -2, and then it will be -3. So 1, -2, -3. So we get the same values, okay, over here. So this will be the, anyway, this will be the lower triangular matrix. The upper triangular matrix will be simply the upper triangularize this LU matrix, this one, this LU matrix, upper triangularize command, and then we can now execute it. So this will be the upper triangular matrix. So in this way we have factorized the matrix A into the lower triangular matrix and the upper triangular matrix, represented respectively by L and U. So we can verify it as well. So for this we can write A double equal L dot U. So that if the result of this substitution or the equation will be true, then that means that our answers are correct. So it will mean that we have A over here as this matrix, and we have L as this matrix and U as this matrix. So when we multiply L by U, so we get the A, and then this shows that this equation is true. So that means we have verified that the answers are true. And for P and C, I have already talked about in the previous video clip. So P is the permutation list, which is 1, 2, 3, which is normal in this case, which shows that no rows have been interchanged. And the value of C is 0 is over here. That means these two matrices are quite conditioned for that means this matrix A, the value of C will mean that this matrix A is well conditioned to have LU factorizations. Okay, so this is only meaning of that. Okay, so let's look at one more example. In this case, again we are going to find the LU decomposition, but here now I have chosen a 4 by 4 matrix, and then I have already explained how we can represent the matrices, okay, in the curly bracket format. So this is a 4 by 4 matrix, and then this is its list form, and its matrix form we can represent like this. Okay, so first we input the vectors, the matrices elements in the list form, and then we can convert it into its matrix form. So anyway, the matrix is still named A. Here I will decompose it by the same command as before we have used, LU decomposition A, and then we have got it into the list form, and now we can convert it into the matrix form. So this is the LU matrix, which is, of course, is the our basis for the finding the L and U matrices. So our L matrix, as we have done before, we can find by lower triangularized matrix with this parameter -1, which shows that we don't want the real values, or for example 2, -1, -3, 4 on the diagonal for the lower triangular matrix. Instead we want ones. So for this, therefore we have used it -1 over here, and then we have added an identity matrix of order 4. So this will give the lower triangular matrix in this case. And then the upper triangular matrix is simply by the upper triangularize command for LU. So this will be the upper triangular matrix. And if we want to verify it, whether it's correct, so then we can just apply this equation again, because we have already know that A was that matrix, L and U were the other matrices. And then just to check it, then the answer will be true. Okay, so what are the permutations in this case? So for this we can see that the permutations are, permutation list is 1, 2, 3, 4, which is normal. So all there is nothing against the order. Okay, 1, 2, 3, 4. Permutation list is 1 through 2, 3, 4. That means no rows have been interchanged, and the C is 0 in this case. So which means that the matrix which we have used is very well conditioned for the LU factorization. Okay, so that was 4 by 4 matrix. Example 3. So now this example 3 will be a little bit different. Just to be on the safer side, I have cleared the value of A, so that we may not accidentally be using the previous values of A. So now I have defined this matrix A to be a 3 by 3 matrix. So this is the 3 by 3 matrix, and then to make it more clear, this will be its matrix form. Okay, 2, 1, -1, 4, -2, -4, -2, -1, 6, 2, 11. And then I apply the LU decomposition with those three parameters, LU, P, and C. Okay, so once this decomposition has been applied, so what I can see in the results now, there is something different. Okay, especially in this permutation part 1, 3, 2, which shows that in order to find its LU decomposition, in order to find its LU decomposition, the Mathematica command has interchanged third and second row. So that means the third row is now at the position of the second row, and the second row is now at the position of the first row. But you know that in the manual calculations, when we say that if we have to interchange the rows, that means we cannot find the LU decomposition. Okay, but in this case, this LU decomposition command has interchanged the rows. Well, both things are correct. Okay, for example, if you have to interchange the rows, that means we are changing this matrix. This matrix will not be the same. So therefore, we cannot find its LU decomposition if we have to change the rows. But this command is smarter than our manual calculations. So this command assumes that we are allowed to interchange the rows. By allowing the interchanging of the rows, then we may find the LU decomposition. So in this case, this command has found out that this command has suggested that, okay, why not change the row 3 to row 2 and row 2 to row 1, and then I will give you a good answer for the LU decomposition. So this is the only thing, okay, over here. So anyway, so now we can see that the matrix form for this LU is in this case the matrix form LU is this. So you can see that LU is 2, 1, minus 1, and then of course some of the values have been changed. So from this matrix form, now we can find the lower triangular matrix by this command. Okay. And we can see that the lower triangular matrix will be 1, 0, 0, 3, 1, 2, 3, 1, minus 2. So here that shows that it is not corresponding to that one. Okay. So if because now these two rows have been interchanged, so 6 divided by 2, 3 has come over here. Okay. So this means that what we are doing is now we are finding the LU decomposition for a other changed matrix. So this P was now 1, 3, 2, as we have already discussed. The rows second and third rows have been interchanged. And here we have this C. C is 0, so which means that the matrix is well conditioned for the row interchange. Okay. Now the upper triangular matrix will be this by this command. And in this case, now if we want to verify it, okay, so for the verification, then of course the verification we cannot perform by the perform with the sorry, where is this, with the original matrix. Okay, this is the original matrix. We cannot perform the verification with the original matrix because now the matrix has been changed. So since the matrix have been changed, so therefore we have to define a new matrix. So this new matrix have been defined something like this. So these are some of the placeholders for the permutations of the rows. So for example, A1 within these two subscripted square brackets, A1, A3, and A2 shows the rows of this column A. Okay, A is from the rows for the rows of A. So it shows that our new matrix is now the one which have the same first row as column as matrix A. The third row, the second row is the one which will be the third row of the matrix A, and the third row is the one which was the second row of the matrix A. Okay, so this is the new matrix. So and it's a matrix form, matrix form A new. This matrix form A new will be this. So this is this will be the one. This is the new matrix 2, 1, minus 1, 6, 2, 1. Originally this row was the third row. This. So so our answer, which we have found from the LU, will correspond to this new matrix. Okay, it will correspond to this new matrix. So this we can verify, and then it will show that it is true. Okay, so this was some small tutorial about the LU factorizations. The LU factorization for rectangular matrices can be also performed, but for those matrices we need to have the elementary row operations. That LU decomposition command will not work, and will give the error. Okay, but anyway, here our discussion is only for the square matrices, for which we are going to find the LU factorization.